Chapter 6 is entitled Thermochemistry, Energy Flow and Chemical Change. And kind of inherent to this chapter is really thinking about how energy gets changed as both physical and chemical processes occur. And so, as we have with all of our chapters split into 5 skills, the first concept is kind of thinking about thermodynamics qualitatively. No sample problems that we'll work on for this, but conceptually we want to think about the fact that kind of this first law of thermodynamics states that energy cannot be created or destroyed. It's simply converted into alternative forms, or said another way, transferred between system and surroundings. And we're going to see examples of this when we have both physical changes and chemical changes. This energy really can be thought of as heat and work. And although there are a few homework problems that kind of deal with that, we don't have a sample problem that we're working on with regards to that. Because this chapter is kind of entitled Thermochemistry, and thermo meaning heat, we're really going to be considering this branch of thermodynamics where heat involved in chemical and physical changes is really the bulk of the energy changes. So the first skill that we'll do a sample problem is thinking about enthalpy. And again, enthalpy is heat in a reaction. So exothermic reactions release heat, endothermic reactions absorb heat, and so we're thinking about heat changes that happen with both physical and chemical processes. And so when we write thermochemical equations, they're just balanced chemical equations that include a change of enthalpy with it. So delta H, again having units of kilojoules, is going to have 2 pieces of information that are relevant. The sign, and again the sign has to do with whether the process is exothermic or endothermic, and then the magnitude, and again that's proportional to the amount of substance that we have. And again, the amount of substance is going to correlate to the amount of heat that's either taken in or given off. And because there's a relationship between kilojoules and quantity, we have this concept of thermochemical equivalence, which allows us to have one more piece of information to walk between moles and a quantity of something. In this time it's a quantity of heat that's either taken in or given off by a chemical reaction. When we introduce this concept of enthalpy, they tell us about manipulating these thermochemical equations, and that's going to become important for Hess's law. So I'll kind of review this again as we get to Hess's law. But 2 things that you can do with thermochemical equations is you can flip them. And if you flip these, they change the sign, making exothermic reactions endothermic or vice versa. Or you can scale the coefficients, and again, that changes the magnitude of delta H. And as we just learned about, those are 2 pieces of information that's important for a thermochemical equation. So how this becomes fairly relevant is we get a new kind of piece to walk between in our mole game. All right, so now there's 5 ways that we know to walk between moles. If you know the mass of something, you can walk to moles with molecular weight. If you know the volume, you can walk to moles using molarity. If you know the quantity of something, you can walk to moles using Avogadro's number. If you know information on pressure, volume, and temperature of the gas, you can use PV equals nRT to walk to moles. And lastly, now that we know the heat of the reaction, we can walk to moles using delta H and that concept of thermochemical equivalence. So we'll have a sample problem here that deals with enthalpy, but the bulk of the rest of our sample problems deal with the last 3 subjects here, which are heat capacity and Hess's law and standard enthalpies of formation. So to just kind of give you a preview of kind of how those fit into everything here. Heat capacity is an experimental way to measure delta H. So what you'll have is you'll have some type of a physical or chemical process that we'll call the system that exchanges heat with the surroundings. And so we'll either see an increase or a decrease in the temperature of the surroundings. And using an equation like this, heat equals the specific heat capacity of the substance times its mass times the change in temperature, we can relate heat that's given off or taken in by a system with heat that's taken in or given off by the surroundings. And so again, calorimeters are ways to experimentally measure this. So again, this is an experimental way to determine delta H. So lots of sample problems dealing with this and kinds of different ways that we can experimentally determine delta H. The last 2 sections here deal with empirical methods or calculation-based methods for determining delta H. The first is Hess's law, and it basically says if you want to figure out the delta H for an overall process, if you sum up the delta H for individual processes that add up to your overall process, you can do that. So again, you're going to see this type of problem when you have a bunch of equations, each with delta H values. You're going to rearrange some or manipulate them to get your target equation, do the same thing to their delta H values, and you'll get that new delta H. So we have one sample problem that we'll practice with that. And then standard enthalpies of formation, kind of two skills that are important within this concept is kind of writing these standard enthalpy of formation equations. So again, we'll deal with that in one of our sample problems. But standard enthalpies of formation can be used as an empirical method to determine delta H, and that's where we're going to be given one equation, and you're going to want to use Appendix B and values of delta HF from Appendix B to calculate your delta H for your reaction using this equation here. Okay, so that's kind of, a brief 5 or 6 minute overview of the chapter. We're going to go ahead now and we're going to work on this first problem that deals with enthalpy. And what we're going to do is draw an enthalpy curve. So again, an important skill to think about is how we draw an enthalpy curve. So first equation here is hydrogen gas plus oxygen gas gives us liquid water plus 285.8 kilojoules. And the process, or this problem, tells us to determine the sign of delta H, state whether the reaction is exo or endothermic, and then draw an enthalpy diagram. So a couple of things to think about here is when we show heat as a product. So again, heat as a product. Anytime you see heat as a product, and this is going to become an important concept that we'll revisit in Gen Chem 2, you can treat heat as a reagent, and a reagent means either a product or a reactant. We can treat heat as a reagent, and when heat is a product, meaning heat is given off, that means this process is exothermic. An exothermic process means that we are going downhill energetically. That means that energy is given off, and so that means the sign of delta H is going to be negative. And so remember, delta H is going to be equal to the enthalpy of our final state, which is going to be our products, minus the enthalpy of our initial state, which is our reactants. And as we'll see here in just a second, we'll confirm this with an enthalpy diagram. Delta H is going to be equal to a negative number when we have something that's exothermic. So again, we'll revisit this in just a second as soon as we draw our enthalpy diagram. So here's how you draw an enthalpy diagram. It's basically sort of like a graph where we're going to have enthalpy on what is sort of like our y-axis here, and enthalpy is H. Make sure not to write delta H here because delta implies a change in substances. We're not showing the change yet. We'll show in just a second how we reflect change. See if this makes sense here. So we have our reactants, 2 species here, and our product, 1 species. What we're going to have when we have an enthalpy diagram is we're going to draw 2 lines. One of them is going to be for our product, and one of them is going to be for our reactant species. And what we need to do here is figure out who goes where. And the difference, the magnitude and the height difference between these 2 lines represents 285.8 kilojoules. But the question is trying to figure out, are we going uphill or downhill? Well, I already kind of told you we're going downhill, but see if this makes sense as to why. If we have reactants that are at a certain energy level, that all of a sudden become products at a certain level, and we have extra energy that we give off as heat, that must mean that our reactants are at higher energy level than our products. So reactants must be up here, and products are down here. The only way to take reactant species, become product species, and have extra energy to give off is if we draw our enthalpy diagram like this. We draw an arrow like this. Arrows are always drawn from reactants to products. And again, just confirm over here, if we calculate a delta H, if we take the enthalpy of the products, okay, the enthalpy of the products here is going to be a smaller number than the enthalpy of the reactants. So this is going to be a larger. Just mathematically, if you subtract a larger number from a smaller number, you're going to end up with something that's negative. So just another little confirmation that exothermic reactions will have an enthalpy diagram that looks like this, and delta H is going to be negative. Okay, so let's go through problem B then a little bit more quickly now that we understand the nuts and bolts of an enthalpy diagram and what it means. So this problem, we've got 40.7 kilojoules plus liquid water gives us water vapor. So again, mapping on kind of the same information that we see up here. Here we're going to have heat as a reactant. Heat as a reactant means we're putting heat into the system. So this means it's endothermic. We can think about this as being uphill. And delta H in this case is going to be positive. So drawing an enthalpy diagram. So enthalpy, which is H. I'm going to draw my same two lines, and since we're not really comparing these, it doesn't matter, you know, what the size of the energy difference is between these. But I know that the magnitude of this difference for this problem is 40.7 kilojoules. Because I need to put heat in, that must mean that my reactants are here. I put 40.7 kilojoules of heat in to convert my reactants into my products. Okay, that energy being put in again means it's an exothermic reaction. If we kind of do the same treatment here, delta H equals HF minus HI. So delta H equals HF minus HI. The final is going to be a larger number. HI is a smaller number. So again, the final being the products, initial meaning the reactants. Delta H of a larger minus a smaller number is going to equal a positive value. And so that, again, is a good reminder that endothermic reactions, where we're taking reactants and elevating them to a higher energy level in products, are going to be positive for enthalpy.